Hello, welcome to this lesson in the linear algebra tutor. As I said before, we're going to continue making that connection between vectors as matrices or as n-tuples in terms of linear algebra. And so here we're going to talk about the vector norm, or what we talk about in another way of saying it is the magnitude of a vector, the representation of a vector and calculating its magnitude. This is stuff that you've probably done in another class in the past, but we're going to use the notation of linear algebra so you can get used to the idea of representing a vector basically as a list of numbers, which is a matrix, which is what we call an n-tuple in linear algebra. So let's draw a few pictures first, because I think pictures make things very, very easy. When we have a general vector, a two-dimensional vector. Let's stay in 2 dimensions for a while to make it easy. So there's the x-axis, there's the y-axis. And we have some vector, which remember means magnitude and direction. So the length of this arrow, the length of it represents the magnitude. That could be the magnitude of the force. It could be the velocity of the wind. It could be anything that has a magnitude or a strength associated with it. The direction the arrow is pointing obviously represents the direction that that wind is blowing or that that force is pushing or whatever other vector it is you're talking about. So we're going to represent this vector as the lowercase a with a bar on top. That's typically what's done. And in this particular case, the tip of the vector here is located at the point 2, 1, right? And that's how we decide, that's how we represent where the arrow is pointing. If it's pointing down here, then the numbers that are associated with the tip of the arrow will be different. Now, the way we analyze vectors, when we think about physics and such, is you look at the projection of this vector along the x-axis. And in this case, this dimension from here to here from the origin, this is 0, is 2 along the x direction. And if we look along the y direction here, this is the number 1. So you see what we do is when we represent a vector on a coordinate axis like that, really all we care about is the tip of the vector, the base of the vector is anchored at the origin. The tip of the vector is free to move about. That basically tells us how strong our force is or whatever and what direction it's pointed in. And the way we map it from numbers into pictures is we say, all right, what is the x-coordinate of this arrow? What is the y-coordinate of the tip of this arrow? And we represent this as a pair of numbers. All right? And then because we can say that there's an x and y component of every vector in the xy plane like this, represented by 2 and 1, then we can say that the vector A, we represent it as a vector A. Usually in a physics course, you would see it written down as 2 in the i-hat direction, plus 1 in the j-hat direction. Now this I and j business, don't get too confused by that. All that means is the I goes along with x, and the j is a unit vector that goes along with y. So what it's telling you is 2 units in the x direction, 1 unit in the y direction, which is exactly what we drew on the board. We don't want to use x here and y here because then we get confused because our variables are labeled x and y, our coordinate axes are labeled x and y, and now we label our unit vectors x and y. It's too many x's and y's. So we use I and j. And in 3 dimensions, you'll see that we also use k for the z direction. All right? But in any case, this is how you would see it written in a physics course. Right? Now, that's totally fine. There's nothing wrong with that. It's just that these labels, these I and j labels, are really not necessary because if we know we're dealing with a coordinate, a Cartesian axis, x and y like that, then really the only thing that's important are the numbers, because I'll just know, I'll make a rule for myself that the first number goes with x and the second number goes with y. So this vector, you really could just write it as a listing of numbers, 2, 1, right? And I'll call it a vector. You know, if I don't put the vector here, then I just know that I'm plotting a point in the xy plane. But when I denote it as a vector with a bar on top, then I know that when I'm plotting is the tip of the arrow. The arrow stretches from the origin to the point, right? So this is a more compact way of writing this, totally fine, all right? But I know now that I'm dealing with linear algebra that I can also represent this vector equally as a capital letter. Usually I denote matrices with a capital letter, and I'll put a square bracket, I'll drop the comma, and I'll just put the numbers, 2 and 1. All right. Now, whether or not I put it as a column or as a row doesn't matter too much for now, but for right now I'm writing as a column matrix, and I need you to start to realize that all 3 of these representations for how a vector looks and is written down are really the same thing. The first one is kind of blowing it in all of its glory, writing down the unit vectors in x and y along with their components. That's great. All right. But I can also shorten that to just an ordered pair of numbers with a comma. Sometimes you'll see this written in a linear algebra book to represent a vector, but I can also dispense with that and just put it inside of a matrix with no comma at all, because really the numbers are relevant, and I know that the number 2 goes with x and the number 1 goes with y. All right, now the same sort of arrangement happens in three-dimensional space. In 3D, we have the following. Now it's a little bit tougher to draw, but I'll do my best. I'll draw sort of like 2 axes like this with a third one coming out of the board. That's what that represents. This is the x-axis, this is the y-axis, and this is the z-axis. And you know that I've drawn it correctly because if you take x and curl it into y, then your thumb should point in z, and that's how it looks. So this is a triplet of axes, three-dimensional space. And now what I'd like to do is represent a vector, let's say, that points here. And I'll call this vector B. Now it's a little tough because in three-dimensional space I'm drawing on a two-dimensional board. But what I'd like to do is draw little dotted lines to help you, well, that wasn't very nice. Let me draw some dotted lines to help you visualize what I'm really talking about. So here we go here we go here, and then here we go here. So these green dotted lines are only existing to show you that the B vector is cocked up out of the xy plane, but it's also kind of cocked forward away from the z-axis, and you can kind of see that from the projection of the shadow of that vector if it casts a shadow down like that. Now in the three-dimensional case, the B vector requires 3 numbers. So let's call it 2, 2, 3. 2, 2, 3. All right. In the three-dimensional case, the unit vector for x, we call it I, like we always have. The unit vector for y, we call it j, as we always have. And the unit vector for z, we actually call it k. So you have I, j, k, x, y, z. And again, we don't want to use x, y, z all the time for our unit vector labels because it gets confusing. All your variables and everything else are labeled x and y as well. So that's why we use I, j, and k. And these little arrows are just little vectors of length 1 that point along the different axes. That's all it is. All right, and so when we have an arrangement like this, following along from before, we can write our vector in 3 ways. We can say our vector is 2, a component of 2 in the I direction, plus 2 in the j direction, plus 3 in the k direction. Notice that the point here, the tip of the arrow is at 2, 2, 3, 2 in the I direction, 2 in the j direction, 3 in the k direction, x, y, and z. That's perfectly fine, but you can also shorten this, as you'll see many times in linear algebra books, as we've already said, and you can just put the digits here, same as before. Now, if you cover this up and just read this, you might think it's just a point in space, like from geometry. But when you put B vector and set it equal like this, you're implying that there's an arrow that stretches from the origin to that point. So the location of these coordinates basically dictate the length of the arrow and its direction. But in linear algebra, we're very much going to drop as much as we can and write everything as a matrix. So I'm going to make a capital B now. That's typically what we do. And I'll make it 2, 2, 3. I drop the commas, I put it in a column matrix. This is a perfectly valid way to represent a three-dimensional vector. 2 in the x direction, 2 in the y direction, 2 and 3 in the z direction, or I, j, k components, as we have always done. I'm just trying to make that connection for you. It's pretty simple, but you need to start getting used to the idea of seeing column vectors or column of numbers or in tuple in column form as a matrix, basically. That's what you need to get used to doing. Typically, you'll see this with the parentheses referred to as an in tuple, and you'll see this referred to a little bit more commonly as a vector. But really, in the context of what we're talking about, they're the same thing. All right, so now we want to talk about the norm of a vector, also called magnitude. Usually when I refer to the length of a vector, the length of that arrow, I'm usually going to say the word magnitude. But in most linear algebra books and a lot of math books, you'll see it referred to as the norm. But in your head, when you see norm of a vector, you should just think magnitude, which just means, that means how long is that arrow? How strong is that force? How fast is that wind speed? Irrespective of the direction, I just care about how long the thing is. What's the magnitude? What's the length of it? That's what I care about. Now, if you remember back from your geometry classes, if you have a triangle, we'll put our vector here like that, as the hypotenuse, we can form a right triangle here. And if we label this C, A, and B, we have a nice right triangle. We can, of course, use the Pythagorean theorem, which is very simply C squared is A squared plus B squared. So if we notice I have an arrow at the tip of my vector, so the length of this hypotenuse really is the magnitude of the vector I care about. But since it forms a right triangle with A and B here, I can represent the length squared of this vector as A squared plus B squared. All right. Now, also, I want you to recall for a vector u, I want you to recall the following thing. We talked about the dot product a little while ago, u dot u. Remember we talked about that. You can basically multiply, if you have a vector dotted with itself, really what we did a little while ago is we dotted a vector with a different vector, a dotted with b. But what we really did in those cases is we looked at the x components and multiplied them together, the y components and multiplied them together, and the z components, and we multiplied those together. And I show you how that was really just matrix multiplication because you add it all together and you arrive at a single number. That's called the dot product or the scalar product. But if you take a vector and dot it with itself, then what you're really doing is you're multiplying its x components time its x component 2 times. So you're squaring the x component, you're squaring the y component, you're squaring the z component. So what you end up having here, if I represent this vector as a comma b, that's component a, component b, or component along x, component along y, and I'm dotting it with itself. So I'm dotting a vector with itself. This is number, 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 number there. Then what I'm going to have is I'm going to multiply the x components together, and I'm going to multiply the y components together. All right, so by dotting a vector by itself, basically I get a squared plus b squared, which equals c squared, and I'm going to call that norm of the vector squared. All right, these double bars here, it's called the norm of a vector, which means the length of the vector, also called the magnitude of the vector. You know, normally in algebra class, when you want to find the absolute value of something, like absolute value of -1, you put bars on both sides of the numbers, just one bar. But for a vector, you also want to know the magnitude or the length of that vector, irrespective of its direction. But for vectors, we put 2 bars, just to kind of remind you that you're taking the length of a vector there, instead of the length of like a number from basic algebra or pre-algebra class. So don't let the double bars scare you. The double bars just means, hey, we're finding the length of this vector quantity in the center. So notice what we do. We dot the vector with itself, and what we end up with is the magnitude of the vector squared. The magnitude of the vector squared. It's a useful thing for you to remember. And so what I'll do is I'll turn it around then, and I will say, thus, usually we write that kind of thing in books, the magnitude of a vector, or what we call the norm of a vector, is equal to the square root of a squared plus b squared, which are the x and y components, but that's also equal to the square root of u dotted with itself, the vector dotted with itself. So this is the norm of a vector. So what this basically says, and I'm going to do a couple problems to show you in a minute, is if you know what a vector is, in other words, if I know the x and y components of a vector, and I can, of course, write them as a column matrix of just numbers if I'd like, then all I have to do is dot the vector with itself, right, and then take the square root, and that's going to give me the length of that vector, right? Because it all boils down to the Pythagorean theorem. When you dot the vector with itself, what you were doing is multiplying x component times x component times itself, so you're squaring it. And then for the y component, you're multiplying it by itself, so you're squaring the y component. So you're basically doing this right here, and then you take the square root of the result, which gives you c, which is the length of the vector, or the norm of the vector. All right, and so what I'd like to do at this point is do a couple of quick examples here. So let's say, I have a little example here. Let's say I'm given a vector, capital U, and I'm given it in a vector kind of notation as a column matrix like this. So that's my vector. The x component of this vector is 1, the y component is -1, the z component is 3. That's kind of implied by the fact that we're using a Cartesian XYZ system. And let's say I want to find the length of this guy. What is the length? If I could put a tape measure and measure it, or if it's a force, what is the amount of newtons of that force or whatever, then what I would do is I would say the magnitude or the norm of the vector u, right, is equal to the square root of the vector dotted with itself, right? So I carry the square root, make it long. Now I'm going to dot this vector with itself. And I know from the dot product that all I do is I take the x components and multiply them together. So it's going to be 1 squared. The y component's multiplied by itself, so it's going to be negative 1 squared. This is because I'm dotting the vector with itself. And the z component is 3 squared. And so what I'm going to end up having is under the square root, this is going to give me 9, this is going to give me 1, this is going to give me 1. So 9, 10, 11 is going to be the square root of 11, which I can put in a calculator and get a number. But effectively, this is the magnitude of u. The magnitude of the vector is the square root of 11. So you see, if you know what the vector is, including its components, you can always calculate its magnitude. And you're doing that by basically squaring the x component, squaring the y component, squaring the z component, adding them up, taking the square root. That effectively is the Pythagorean theorem in three dimensions, right? And what that is equivalent to is dotting the vector with itself and taking the square root. Because when you dot the vector with itself, what you are doing is squaring the components. That's what the dot product's doing when you apply it to the same vector, when you dot the vector with itself. All right, so as another quick example, here I was given a vector in terms of a column of numbers. What if I'm giving the vector in terms of an n tuple? Right, so let's say I'm given v is equal to negative 2, 1, negative 2, 4. Now notice in this case, this is an n tuple, and I've got 4 numbers. So this is not two-dimensional space, it's not three-dimensional space, it's four-dimensional space. What is four-dimensional space? Your guess is as good as mine. You could use this as a space-time. This could be x, y, z, and time, for instance. That's four-dimensional space that we live in. But really, mathematically, I guess what I'm trying to say is it doesn't really matter. You can still calculate the length of this vector in 4 dimensions. You're just applying the same thing and extending that definition to all of the components. So if you want to find the length of that vector, we could just proceed straight to the answer, but I'll remind you that if you were going to write that vector as a column matrix, it would just be negative 2, 1, negative 2, 4. So this could be x, y, z, and some other dimension, maybe temperature, maybe time, something else, some other number that needs to be represented there in the space that I'm working with. All right, and then if I'm going to find the magnitude of the vector v, what I'm going to do is I'm going to take the square root of the vector dotted with itself, which is the square root of negative 2 squared plus 1 squared plus negative 2 squared plus 4 squared. And I'll extend that square root to cover everything else. Let me switch to black real quick, and what we're going to get is the square root. This 4 times 4 is 16. This is going to give me 4, this is going to give me 4, this is going to give me 1. So what I'm going to get here is the square root of 25. And of course I know what that is. That's just equal to 5. So the length of this vector, which happens to have 4 dimensions, is just equal to 5 in this case. Now, a lot of the concepts that we've been doing in this section are things that you've been probably working with in the past. You've probably been exposed to vectors. You've probably understood the length of a vector. But we're kind of going over some of the ground that you've probably studied in previous courses to put it in the framework of linear algebra. Writing the vectors as column matrices like this, going over the vector magnitude and things. The dotting a vector with itself gives us the magnitude squared so that we can take the square root and get the magnitude. All of those things are important because, as I said before, as we go forward in linear algebra, we're going to cover a lot of material, but eventually we're going to get to vector spaces way in the future. And what that is going to be all about the study of these vectors and these coordinate systems and how to translate them and how to rotate them and how to manipulate the vector space. So we're kind of covering some of the basics of vectors now in terms of linear algebra so that when we get there, you're not scratching your head. What's a normal vector, so to speak? So that's what I wanted to cover here. Make sure you understand this concept. Make sure you understand the dot product of a vector. And most importantly, whenever you dot a vector with itself, you are in effect squaring the components of the vector. Right? So you're arriving at the magnitude squared. When you dot a vector with itself, you're arriving at the magnitude squared. So you take the square root of that guy, and that gives you the magnitude of the vector. Make sure you understand that. Follow me on to the next lesson, where we will talk about unit vectors in linear algebra.